So welcome back. This video is the first of the migration model videos. So recall I said that when we want to estimate lifetime value, one big distinction we make is between gone for good and always a share. So in the gone for good situation, we assume that once the relationship ends, and it ends in a bang, the customer never comes back. And we've already studied things like the simple and the general retention model and using survival analysis to study those situations. Now, always a share, on the other hand, makes the assumption that customer inactivity during a certain period doesn't mean the relationship is over. So if this is a retailer, if I don't buy from Eddie Bauer this month, that doesn't mean I'll never come back again. To use the migration model, what we're going to assume is that there is some finite number of what are called states. Now, you can also think of these states as being segments. We're going to assume that the customers migrate between these states over time. So I could be in one state now, and next month I'll be in another state. To give you a concrete example of this, maybe one state is having just purchased while another state is being inactive. So if I go from being inactive to being active, then I have migrated from one state to another. Alternatively, I could just stay in one of these states, but over time. So this model tends to get used across a lot of different industries, from travel. So if you're modeling hotel or airline or something like that, we're going to use it. Retail, automotive, electronics, appliances, and also nonprofits. So as I just mentioned, we're going to assume discrete states or segments. We're going to label these usually 1, 2, 3, 4, although maybe we will start at 0, so 0, 1, 2, 3, whatever, depending on the situation. So random variable x sub t is the state that a customer is in at time t. Now, we could add a subscript and make this x sub it, because we could have different random variables for each customers. But so in order to avoid having too many subscripts, we will take x sub t as referring to a single customer. We're going to assume something called the first order Markov property. What this property says is that the probability distribution of which state I'm in right now only depends on where I was one period ago. So what happened prior to that is irrelevant. So we can write that in using notation as follows. So the probability that I'm in some state in period t plus 1, given all my history, where I started out, where I was in period 1, period 2, all the way up through the previous period, this probability distribution is the same probability distribution as if I only told you where I was in period t. So what happened prior to period t doesn't matter. So here's the way we're going to develop the migration model. In this video, I am going to start with the simplest of all possible migration models, one that only has 2 states. And we'll do a very thorough job of understanding that 2-state system. In the next video, I'll show you how we can expand this to more states. So I like to call this the simple buy, no buy model. I think it might be better if I did this off on my scratchpad. It's probably a little bit more interesting for me to do this live rather than just talk over the slides. We're going to start by assuming that at time t, some customer. Now, if you want a subscript, we can call that subscript I. So I will index customers and T will index time. Either buys or not. So those are going to be my two states, buy or not buy. So if you want to use the concepts from elementary probability theory, you could say let B sub t equal the event that the customer buys at time t. So during month t of my life, I decide to buy an airline ticket from American Airlines. Then, of course, BT with a bar over it would be the event that the customer does not buy at time t. All right. Now, we will also assume this. So we could write this as follows. So we're going to assume the probability that a customer buys in period t plus 1, given that they just bought in time period t. Now, if you want to use the x notation, you can write this as follows. This is going to be the probability that x t plus 1 is equal to 1, given x sub t equal to 1. So given that I just bought, what's the chance that I buy again, is the way to think of this. We're going to denote this by the letter P1. Likewise, the probability that the customer buys at time t plus 1, given that the customer did not buy in the previous period. So you can write this as x t plus 1 equal to 1, given x sub t is equal to 0. So given that I didn't just buy, the probability that I buy again, we're going to call P naught. Now, whenever we have these Markov chain models, it's rather than using all this notation, it's much more convenient to draw out something called a state diagram. So in this case, we have a buy state. We can think of this as state number 1. And we also have the non-buy state, which I'm going to call state 0, just because usually when we have a dichotomous variable, we tend to make it a 0-1 variable. 1 means you buy, 0 means you don't. Now, what can happen is that next period, someone who starts out in this buy state might decide to stay. So that's going to happen with probability P1. Alternatively, somebody who's in this buy state might decide not to buy, in which case that customer migrates to the non-buy statement. That's going to happen with probability 1 minus P1. Well, what could happen to a customer who starts out in the non-buy state? Well, clearly, this customer could decide to buy, and that's going to happen with probability P naught. So this is given that I start out in the non-buy state, what's the chance that I come back to being active? Well, the answer is P naught. Alternatively, a customer in this non-buy state could decide to stay inactive, and that's going to happen with probability 1 minus P naught. So this is our state diagram, and I hope that makes it very clear what's going on. Now, what's going to happen next is that we will allow ourselves more states. For example, maybe we want to define our states based on recency. So this would be a customer who just bought. This might be someone who has been inactive 1 month. This could be a customer who's been inactive 2 months, 3 months, 4 months, and so forth. But more on that in the next video. At time 0, we're going to assume the following. Assume there are N1 customers in the buy state. So you have N1 customers who have just bought from you. Perhaps there are also some customers, in fact, N0 customers, in the no buy state. A few more assumptions. We're going to keep the model extremely simple, but you could make this more complicated if you like. We're going to assume that we spend C dollars on marketing each period. So maybe I invest in some contact points, and the cost of those contact points, for example, I could send out a catalog, a paper catalog to this customer, or I could invest in a sales call. The cost of that is C dollars. We're also going to assume this. Assume the net contribution of a customer who buys is M dollars. Now, let BIT equal the value of customer I at time t. Now, again, I'd rather not carry around all the subscripts, so I'm just going to call that VT much of the time. So notice that VT is equal to M minus C if X sub T equals 1. So if a customer just bought from you, you get the M dollars from the order less the marketing costs, while the customer who doesn't buy from you is worth minus C. So if at time T, I decide not to buy, then you've spent C dollars on me without getting any return. Now, as I said, you could make this more complicated and add a subscript to the C's. For example, you might want to spend more on your active customers than your inactive customers, but we're not going to go there now. So having set up all this notation, we're going to answer one big question, but we're going to do it by answering 3 questions that lead up to it. So I'm just going to start with the last question we're going to ask, which is, what is the customer equity of this database? So I've got a database of N1 plus N0 customers. This system, this thing is going to run off into infinity. What is the customer equity of this? Well, the answer to that is going to be as follows. So let's just say that CLV sub I, it's a sub I, not a T. Let me rewrite that to make it really clear. CLV sub I is the lifetime value for customer I. So remember the definition of customer equity. So customer equity is just going to be the sum over all the customers I've got. This would be, I've got N0 plus N1 customers. Just add them up. So that's easy. So if we can know what these CLV sub i's are, then computing customer equity and answering this question 4 is easy. Well, that leads to how to find CLV sub I. Well, in order to answer that question, let's go back to the definition that I gave you of lifetime value on the very first day. So CLV is just the sum T, that's a T equals 1 to infinity. Let's take the expected value of the customer at time T, and we're going to discount that, 1 plus D raised to the T, where D is the, I like to call it the period discount rate. Now the question is, what is the expected value of a customer at time t? Now notice I could stick in a subscript here if I wanted to, but let's not. So that's going to lead us to question 2, which is how to find the expected value of v sub t. This isn't too bad either. The expected value of a customer at time t is going to be this. So if we look up here, I get m minus c dollars whenever this is true. So we're going to write this as m minus c times whatever that probability is. So the probability that x sub t equals 1 given wherever you started. So we're going to need to know where you start. But then notice the other thing that could happen is I lose c. Well, what's the chance that I lose c? I lose c with probability, well, when the probability of xt equals 0 given wherever you started. All right, so we're almost there. Now we have the hard question, because we need to find these quantities. So what are those quantities? So we're going to write this as question 1. How to find the probability of xt given x naught. Now, as I say, this one's a little bit more involved. Let's start out really simple and suppose t is equal to 1. Now, I claim this is completely trivial. If t is equal to 1, we can think of, well, the probability that x sub 1 is equal to 1 given x naught equal to 1. That's just p1. Likewise, the probability that x1 is equal to 0 given x naught equal to, if I start out in the no buy statement, the probability that I don't buy again is 1 minus p naught. You've got a couple more possibilities. So what's the probability that x1 is equal to 1? Given that I start out in the no buy state, this would be p naught, and then the probability that x1 is equal to 0, given that I was in the buy state, will be 1 minus p1. Now, we will write this as a matrix. It's going to be much more convenient to think of this as a matrix, and we're going to call this matrix P. So P is going to look something like this. So here's our matrix. I like to think of this as time 0. So you're either in the buy state or the non-buy state. And then at time period 1, you will go to the buy state or the non-buy state. So if I start out in period 0 in the buy state, the probability that I buy again is P1. The probability that I decide not to buy the next period is 1 minus P1. This probability is P naught. This is 1 minus P naught. All right, so this is very compact notation. We can just write this as a matrix P, which is a 2 by 2 matrix clearly, that shows in the rows where I am in the previous state, in the columns where I go in the next state. Let's take this up a level. Suppose that t is equal to 2. Now, I have to warn you, the next 2 or 3 minutes are going to be kind of tedious. So if you'd rather just kind of skip ahead or watch this at twice the speed, I won't be offended. Let's start out by assuming that at time 0, I am a non-buyer. Now, the easiest way to see what's happening is to draw a probability tree. Go back to your elementary stats class when you did Bayes' theorem and you drew lots of these. So if I'm a non-buyer, there are two things that could happen. In period 1, I could either buy or not buy. And let's write those probabilities. So if I start out in the non-buy state and I buy, that happens with probability P0. This would, of course, be 1 minus P0. Now, let's go see what happens at time period 2. So there are two possibilities. So either I buy or I don't buy. And both of those possibilities exist if I'm in the top part of the tree or the bottom part of the tree. So if I'm in the top part of the tree, I go up this ladder. So notice I just bought. So this is going to happen with probability P1. And we multiply across. So this is going to be P0, P1. So that will be the probability that I buy. And then I buy again, given I started out in this non-buy state. Well, what happens here? This is 1 minus P1. So the probability that I buy and then not buy is P0 times 1 minus P1. Then what's going to happen down here? Well, notice I'm in the non-buy state at this point. So this means I go up with probability P0. I go down with probability 1 minus P0. This will be 1 minus P0 times P0. This will be 1 minus P0 squared. So now we know the probability distribution going 2 periods out if I start out in the non-buy state. So the sum of these two values give me B2. So I'm in the buy state in period 2, whereas the sum of these two probabilities give me not B2. Let's do the same thing. I warned you this was going to be tedious. Feel free to jump ahead. But what happens if I start out in the buy state now? So I'm a buyer in period 0. In period 1, there's two things that could happen to me. I either buy or I don't buy. I go up the tree here with probability P1. So I just bought. The chance that I buy again is going to be P1. I'm going to go down with probability 1 minus P1. Now let's get to where I'm at period 2. So I either buy or I don't buy. Notice I'm sitting in the buy state, so the probability that I buy again is P1. The probability that I don't buy is 1 minus P1. We can write out the joint probability. So what's the probability that having started in the buy state, I buy and I buy again? That's going to be P1 squared. So this number times this number. What's the probability I buy and then not buy? Well, P1 times 1 minus P1. And we can do the same thing down below. So we have B, B0. So here, notice I'm inactive. I'm in the non-buy state. Well, what's the probability that I buy again? The answer is P0 then. Because I'm in the non-buy state, we're going to put the P0 rather than P1 there. This is going to be 1 minus P0. So what's the joint probability that having started out in the buy state, I don't buy, then I buy? The answer is 1 minus P1 times P0. I'm going to be probability 1 minus P0. Now, you should feel exhausted at this point because that was a lot of work. So it turns out there's a much easier way to get these probabilities, and I'm going to show it to you in a second. Actually, before I do that, let me just point out the sum of these two would be B2. The sum of these two would be not B2. So how can I get these probabilities in a simpler way? Well, the answer is this. So I'm just going to call this a theorem. I'm not going to prove it, but the k-step transition matrix is p to the k. So that is going to make our life really easy. So let's just check it. So check for k equal to 2. So if I want to know where will I be 2 periods from now, the answer is go find p squared. So let's do that. So what was my p matrix? Well, here's my p matrix. It's going to be 1 minus p naught, 1 minus p1, p1, and then I just got to copy the same thing again. So 1 minus p naught, 1 minus p1, p1. I'm now going to do the matrix multiplication. And if we want to find the top left entry, I made a mistake. This is going to be 1 minus p naught squared plus p naught times 1 minus p1. So this times this plus this times this gives me that entry. So now the way to think about this is time 0. So state 0, state 1, and we can think across the top. This is time equal to period 2. This is no by, this is by. So if we start out in the non-by state, what's the probability that I don't buy? Well, it's going to be 1 minus p naught squared, so those two match up, plus p naught times 1 minus p1. Okay, well, let's go do the top right entry. So this one is going to be 1 minus p naught times p naught, so that times that, plus p naught p1. Well, let's go check this out. So what's the probability that if I started out in the non-buy state, 2 periods later I'm a buyer? Well, it's going to be 1 minus p naught times p naught, and then p naught times p1. So it looks like this is working out. Well, let's go do the others. So what's the lower left? So if I start out as a buyer, what's the chance 2 periods from now I'm not a buyer? Well, this is going to be 1 minus p1 times 1 minus p naught, plus we're going to have p1 times 1 minus p1, and let's go see. So if we go look up here, that's going to be 1 minus p1, and I think I made a mistake up here. Clearly I did. 1 minus p1 times 1 minus p naught. This should be 1 minus p1. So that's coming from here, that's coming from here, and sure enough, that's what we end up with. So this, and then we end up with the other term. Sorry about that. Well, let's go do the other cell here. So I start out as a buyer. What's the probability 2 periods from now I end up as a buyer? This will be this number times this number. So 1 minus p1 times p naught plus p1 squared. So let's go check this out. We have 1 minus p1 times p naught, and then p1 squared. So my point is simply this. I can find out where a customer is going to be k periods from now by computing a matrix product. And this will work. What I would maybe encourage you to do is, if you're not really fully grasping this, try it for t equal to 3. So if you check this out on another period, there will be 4 ways that you can be a buyer and 4 ways that you can be a non-buyer. And then try it with the matrix multiplication approach. You will get the same answer. So a few more things to know. So let's finish putting this into matrix notation. So remember, at time t equal to 0, we assumed that there were n naught customers in the non-buy state and n1 customers who started out as buyers in this first period. We're going to write n naught and n1 as a vector. It's called the initial vector, and this is what it looks like. And of course, n transpose will just be that as a row vector. Here's our probability matrix. One thing to note about transition matrices is they have rows that sum to 1. So if you take p times 1, you get 1. In other words, 1 minus p naught plus p naught has to equal 1. 1 minus p1 plus p1 also has to equal 1. So it looks like we did it right. The other thing that we had was this value, v. And so the value of a customer who buys, remember we said was m minus c, whereas a customer who doesn't buy has value minus c. So you invest c dollars in marketing costs and get nothing in return. So this is the two-step transition matrix that we derived on paper. The k-step transition matrix gives the probabilities of starting out in state I and ending in state j, k periods later. We can answer question 2 in our matrix notation as follows. We're going to take the probabilities in t periods for now, so that's p to the t, and just multiply it by this value vector. So if you think about what I just did, that's a matrix multiplication, where I take the distribution and multiply it by the value vector. And so we can write that very compactly in matrix form as p to the t times v. Then the lifetime value, we just, to get the lifetime value, remember we took the expected values divided by the discount rate, and so now we're just popping in the expected value of these v's. And then to get customer equity, we're going to sum this. Now the question is, how can we simplify this? It's not very nice to have this as an infinite sum. Well, we're going to do exactly the same thing that we did back with the simple retention model when I showed how we could find the sum of a geometric series, but now we have a geometric series of matrices. So let's say that I have some sum of matrices. So S sub t is going to be, we're going to think of this as a to the 0 power plus a squared all the way through a to the t minus 1. So think of this as the first t terms. Since we start counting at 0, we go from 0 to t minus 1. This is going to be the first of the first t terms of this geometric series of matrices. Now, I'm going to post-multiply both sides by a. And so we end up with another geometric series of matrices. If I subtract the second equation from the first equation, so take S sub t minus S sub t times a, I get this. Now I can do the same thing to the other side. I take I minus nothing, and then you have a minus a, those cancel out, a squared minus a squared, those cancel out, all the way through a t minus 1 minus a t minus 1, those cancel out. And then I've got minus a sub t. So I'm taking the top equation minus the bottom equation. I get what's on the right. Now, notice I can factor out S sub t, and then let's post-multiply by I minus a inverse. So if I do that, I minus a times I minus a inverse becomes the identity. So what's on the left-hand side is just S sub t. That's the thing I'm interested in. The right-hand side is going to be I minus a to the t times I minus a inverse. So you can think of this as like, what would happen if these a sub t's went to 0? So if as t goes to infinity, the elements in this A matrix get smaller and smaller, then what we end up with is just I minus A. Now, let's just go over to my document camera. So the usual way we write a geometric series is this, S sub t. We tend to call it R to the 0, which is 1, plus R to the 1, plus all the way through R to the t minus 1. If you take the limit as t goes to infinity of S sub t, remember this is equal to 1 over 1 minus R. So whatever this thing is that's growing geometrically, we take 1 over 1 minus that. And if you look at this, this is basically what we have here. 1 minus the thing that's getting multiplied as we form our geometric series. And the inverse is like sticking it in the denominator. So we've just derived a closed form expression for lifetime value as well as customer equity. So let's start with customer equity. Customer equity is going to be this expression discounted. My initial vector n doesn't have any subscript t in it, so we can just pull that out. Likewise, v has no subscript t in it, so we can pull that out. Now what we're left with is p over 1 plus d. Now, as long as d is positive, what's going to happen is that as t grows, this will approach 0. And we can just go use our sum of a geometric series that we derived up here. And we now have a closed form expression for customer equity. If you want customer lifetime value, this part right here gives you the lifetime value for customers. So I'd like to point out that I derived this for a two-state system, the buy, no buy system, but everything that I did will apply if I had a much larger P matrix. So if I wanted to have, say, 10 states, this same expression would work.